Hey everybody, this is Mrs. Drieski. Thanks for joining us again today. Today we're going to talk about alternating series and conditional and absolute convergence. So let's get started. So far we've only been dealing with series that have positive terms. So if you go and check out the old videos, you'll see that all of those other ones have positive terms. But not every series is positive. So what do we do then? There's a special type of series, it's called an alternating sequence, where every single term is going to change or alternate in between being positive or being negative. So when we graph them, they kind of have some unique looking graphs like these. These types of series or sequences have their own test for convergence. So this is the definition of that test. And basically what it means is that the series is decreasing and the limit of the series multiplied by -1 to the n-1 power, which basically just switches the sign on every term, equals 0, then the alternating series converges. If either condition fails, then there's absolutely no convergence. So let's break it down a bit. This little piece right here, this says that 0 is less than or equal to b sub n plus 1, which is less than or equal to b sub n. So if you have a decreasing series of numbers like 5, 4, 3, 2, 1, kind of like that, what this is saying is, hey, the next number is smaller than the one that came before it. So like we could call this b sub n, and this would be the next number, b sub n plus 1. Now that next number, because this is a decreasing sequence of numbers, this next number is actually smaller than the one that came before. And that's all that this is saying right here. This actually defines a series of numbers of being decreasing. I know sometimes the way that these statements are written makes it look a lot more complicated than it actually is, but you've got this. So what this is saying is, hey, as long as it's a decreasing sequence and n exists on the set of positive integers, so this means that n has to be a whole number. And that makes sense, right? And you can't have the 1.5 number in a series of numbers. It's like you've got the first number, you've got the second number, you've got the third number, but there's not like a 5.5 number. So obviously the n value, the number of terms that you have, has to be an integer, a positive integer. And then again, the limit as n approaches infinity has to be equal to 0. And if it does equal 0, then the series is convergent. So this is how we're going to test an alternating series to see if it's convergent. So here we go. Example number 1. So I've got this series of numbers, and I want to show that the sum to infinity of them converges. So we're going to prove this first by showing that the series is a decreasing series. So it is alternating, I can tell, because of this -1 to the n-1 power. I said not n this. So this is an alternating series. Because of that -1 to the n-1's power. And then let's see, our b sub n is like all the rest of the stuff that's here. So that's not this alternating piece. This is the thing that changes our sign from negative to positive, or positive to negative, depending on what value we start with here. So I don't have anything in my numerator, so that's going to be a 1. Because it can't be 0. And then my denominator, I have n. So I'm basically just ignoring the alternating part here, and what's left over is my b sub n. Okay, so it looks like b sub n is going to be 1 divided by n. Well, let's show that this is actually a decreasing function. So what we're going to show is that 0 is less than or equal to b sub n plus 1. Well, b sub n plus 1 is just b sub n with a n plus 1 put in everywhere that an n is. So that's going to be 1 divided by n plus 1. And this has to be true. Is it? Obviously so. If I had an n value that was 5, then 5 plus 1 is 6. So 1/6 is less than 1/5. This is a true statement. So it is true. And so that satisfies the fact that this is a decreasing function. For every single n value that exists on the set of positive integers. If you remember that fancy z with a little plus sign in the superscript position tells us that we're on the set of positive integers. Hey, and I love this 1 divided by n because we know about the limit of that. Okay, so the limit as n approaches infinity of 1 divided by n is equal to 0. So we've just met all of the things that are necessary in order to show that this alternating series converges. We've shown that it's a decreasing function, and we've also shown that the limit as n approaches infinity of b sub n is equal to 0. Therefore, the series converges. And we're done. Not so bad, right? So we use these like fancy notations and fancy definitions, but it's really pretty simple. You're just going to show it's decreasing using the method that we went over, and then you're going to calculate the limit as n approaches infinity. If you get 0, it's convergent. If you don't, it's not. So let's go on to example number 2. Ooh, fancy. Oops. Come back here. There it is. Okay, so let's try it again. First, we're going to check and make sure this is a decreasing function. Okay, so it's got to mean that 0 is less than or equal to the b sub n plus 1 term. So everywhere I see an n, I'm going to put in an n plus 1. So I'm only looking at the b sub n piece. So the b sub n here is the stuff that's not part of the alternating series. So that's going to be n squared divided by n squared plus 5. That means that b sub n plus 1 is going to be n plus 1, plus sign, n plus 1 squared divided by n plus 1 squared plus 5. And that has to be less than or equal to the actual b sub n. So that would be n squared divided by n squared plus 5. All right, so is this true? Well, let's check it out. Let's try an n value. So I tried the n value, n equals 1. You know, if I can show that it doesn't work for one n value, then I'm showing that it's not true, and then it would be not converging. So let's check it out. Let's substitute in an n equals 1 and see what happens here. So I've got 1 plus 1 squared divided by 1 plus 1 squared plus 5. Oops, got to extend my fraction bar. All right, well, 1 plus 1 is 2, and 2 squared is 4. And 1 plus 1 is 2, 2 squared is 4, and 4 plus 5 is 9. Now, 4/9 approximately 44/100ths. So let's check it out and compare it to our b sub n term. So again, I'm going to use n equals 1, and I'm going to sub it in here. So I've got 1 squared divided by 1 squared plus 5. Well, 1 squared is 1, 1 squared is 1 plus 5 is 6. And 1/6 is approximately 16/100ths. Well, if that's the case, then we're saying 44/100ths is less than 16/100ths. But we know that that's not true. So this series, right away, I can tell it's not a decreasing series. It's definitely increasing, at least here. So this doesn't meet the requirements for the converging alternating series. So fail. But just so that you can see that it actually really fails, it super fails, it's going to fail the second test too, which is the limit as n approaches infinity of b sub n. So let's try that too. Oh my. So our second test, or second part of the test, is to calculate the limit as n approaches infinity of b sub n. So our b sub n, again, was n squared divided by n squared plus 5. And the easiest way to calculate this limit is to have a dividing by n squared party. My highest power is n squared. So if I divide every single term by n squared, it's not like I've really changed the value of this function, but it is going to be a lot simpler for me to calculate the limit. So let's do that. I'll have the limit as n approaches infinity of n squared divided by n squared, all divided by n squared divided by n squared plus 5 divided by n squared. Now these are going to reduce, and I'm going to get 1 divided by 1 plus 5 divided by n squared. Calculating the limit of this is pretty easy because there's no effect on the ones. And then the limit as n approaches infinity of 5 divided by n squared is 0. So here I get that the limit as n approaches infinity is 1. And last time I checked, 1 does not equal 0. So this diverges. So it didn't just fail a little bit, it failed a lot. And there you have it. You've got the alternating series test. Now, you can actually also calculate the sum of an alternating series if it does converge. We call that a partial sum to estimate. And because it's just an estimation, because we can't actually literally calculate the sum to infinity of adding up every single alternating terms, there is going to be an error. So the alternating series estimation theorem allows you to calculate the error of your partial sum of the alternating, or any kind of series actually. So let's check it out. Basically, this definition tells you that when you use a partial sum to estimate an infinite sum of converging alternating series, like maybe we would say like the sum of the first 10 terms, then the error that you get from only using that number of terms has to be less than the value of the 11th term, or whatever that next term would have been. So that's what this is all pretty much saying. And I gave an example of the 10th and 11th term. So let's take a series that we've seen before, this guy. And I want to know how many terms of this series are necessary so that the approximation that we get of the sum is within 1/1000th. Okay, so that's a pretty accurate summation. How many terms? Do you have a guess? Like how many terms would you have to add, and would you think, until we have a sum that is accurate within 3 decimal places? Do you have a guess? Well, let's see if you're right. This particular series is going to generate something that looks like 1 minus 1 divided by 2 squared plus 1 divided by 3 squared minus, because it's alternating, 1 divided by 4 squared, and on and on and on it will go. So this is the 1, 2, 3, 4, the first 4 terms, the sum of the first 4 terms. And that's not going to be super accurate. We want to add more and more terms to gain our accuracy here. So what's your b sub n in this problem? So it's the part that's the non-alternating piece. So this -1 to the n minus 1 power, this is what alternates the signs for us. So what's left over is your b sub n. In this case, that is 1 divided by n squared. Great. So what that tells me is that my b sub n plus 1 is going to be 1 divided by, and instead of putting this n in, I'm going to use n plus 1. Don't forget that denominator is being squared, so make sure that you use that square in your b sub n plus 1 as well. So in order to even use any of these alternating series, we have to check that it's convergent. So we can't find a sum if it doesn't converge. So we got to check that it's decreasing and convergent, which means we're going to check to show that 0 is less than b sub n plus 1, which has to be less than b sub n. Is this true? Well, yeah. I mean, the bigger that your denominator is, the smaller your fraction is. So this is definitely smaller than this guy. So this is true. Now let's show that the limit is equal to 0. So the limit as n approaches infinity of b sub n, and we definitely know that this is true. This is 0 because of, well, if your denominator is getting bigger and bigger and bigger, 1 divided by a really big number is going to get closer and closer to 0. So we do know that the sum converges. What I don't know is what it converges to. So I'll just call it S, the sum, by the alternating series test. All right, so now let's check for the error. Whoa. So when I'm checking for the error, I'm going to use the definition that we got before. So the definition that we got before was that r sub n, the error, the amount of the error, is equal to the absolute value of our sum minus the sum of the first n terms. So our altogether sum minus the sum of the partial sum that we would be adding together. So I don't know what the actual sum is, and I can definitely calculate the partial sum, but we want that to be within 0.001, so a pretty small error. We also know that the absolute value of the difference between those sums has to be less than or equal to b sub n plus 1, the next term. Now that was just back in the definition of the alternating series. So I do know that we're trying to keep this within 1/1000th. So I know that this is equal to the absolute value of s minus s sub n. We want it to be, we want that error to be that number or less, right? We want it to be within that amount. So here's what I would say. I would say that we want this error to be greater than the actual last term that we're calculating. Because remember, if the difference between the sums is less than or equal to b sub n plus 1, then the error is also less than b sub n plus 1. And what we want is b sub n plus 1 to be smaller than that if we're going to keep this within this error range. I know that that can be confusing, but we need this error to be less than than 0.001. So let's make that a little note. Our error is the difference between the sums. So we need that to be less than 0.001. And I guess I could probably write this in the opposite order, but it means the same thing. All right, so let's go ahead and pop in b sub n plus 1. We actually figured it out earlier. It's 1 divided by n plus 1 squared. So let's go ahead and use that. So I've got 0. Ooh, interesting color. I was not intending to use that. 0.001 has to be greater than 1 divided by n plus 1 squared. Now I don't really I want to solve it for n. Obviously I don't enjoy having this in our denominator, so I'm going to go ahead and multiply both sides of this inequality by n plus 1 squared. That's going to be nice to get it out of the denominator for us. Fantastic. Now we've got n plus 1 squared times 0.01 is greater than 1. Well, let's go ahead and divide both sides by 0.001. I'm not flipping my inequality because I know this is a positive result, because when you square something, it's going to still be a positive, and this guy is obviously positive, so don't flip your inequality. And I've got n plus 1 squared is greater than, now 1 divided by 0.001 is actually 1,000, so I'm just going to use 1,000. And to solve, we're going to take the square root. So I have n plus 1 is greater than the square root of 1,000. And I'm going to subtract 1 so I can get the n alone. Woo-wee! When I pop this into my handy dandy calculator, making sure that the minus 1 is on the outside of the radical, I actually get that n is greater than 30.622. Now, as you recall, remember n has to be a positive integer. And so 30.622 is not an integer. This is a rational number. And so it's either going to be 30 or it's going to be 31. And since in order for us to have an error that's within 0.001, I have to have n be larger. So this is going to be n equals 31. And what that tells us is that if we want to have a very small error within 3 decimal places, that I have to add up at least the first 31 terms to get that error within 3 decimal places. Now, I have had students say, well, wait a minute, this is less than or equal to, so the inequality sign would have to be flipped. And I get that. This error has to be less than b sub n plus 1. So you could find out what your 31st term is, and that's going to be less than what our error is, and that's going to be correct. But that's just in the definition. I could have also said where the sum is greater than 0.001, and we would flip our inequality. So this setup here doesn't have anything to do really with this situation. It has to do with how this is defined here. You know what I mean? Okay, so now let's move on to absolute and conditional convergence. So we can actually have an absolutely convergent series, or we can have a conditionally convergent series. The difference is that we call a series who converges and also whose absolute value converges. We call that absolutely convergent. So if both converge, it's absolutely convergent. If the series converges but its absolute value does not, then we call that conditionally convergent. So that's all that this is saying here. For example, this is a problem that we have seen before. We've got 1 minus 1/2 plus 1/3 minus 1/4. See, this is our alternating series with 1 over k. Okay, we've shown that this converges. And we also know that the sum of 1 divided by k diverges. That's the harmonic series that we saw when we were investigating the p series. So because the absolute value doesn't converge, because we're taking away all of the changing of the signs here, because the absolute value doesn't converge, but the alternating series converges, then we call this conditionally convergent. Once again, when we look at the alternating series and calculate that out, this does converge. We already investigated this. But when we take the absolute value, the effect of that happening is that all of these signs stop alternating. Instead, they all become positive, and that's going to diverge. It's going to keep on growing and growing and growing. So because the absolute value does diverge and the original, the alternating series converges, that's conditionally convergent. I hope that that made sense. So if you take the term of a convergent alternating series and make them all positive, if it still converges, it's absolutely convergent. If it now diverges, then it's conditionally convergent. This is like the basic understanding of the difference between conditionally convergent and absolutely convergent. Why does that matter? Why does it matter if a series is conditionally or absolutely convergent? Well, we can reorder the terms of an absolutely convergent series, but we cannot do that with a conditionally convergent series. So we need to be able to, in an absolutely convergent series, rearrange the terms without affecting the sum. So let's take one and show you what exactly I mean. All right, so let's take this guy, the one that we've been talking about, and show why the convergence matters. So this was our example number 1 that we did so far in this section. So the first thing that I did here was I stretched it out, my alternating series, right? And I stretched out a bunch of the terms. Is going to continue going off to infinity, so I just stretched it out. Here's where n is 1, here's where n is 2, where n is 3 and 4 and 5, blah, blah, blah. So the next thing that I'm going to do is I'm going to rearrange the terms. So I'm going to switch their order a bit and kind of show you a little way of combining them together. So I've grouped these two together. I moved 1/3 over to the 1/6. So I've got my negatives together, then I've got my 1/3 and my 1/6. So I'm just shifting around the order, but I'm keeping all the signs the same. You know, this was a positive 1/3. Here it is positive. This was a negative 1/6. Still, it's negative. The 1/5 didn't go anywhere. It's back here. Just shifted them around, changing the order. Then I simplified. So everything that's in these parentheses, I simplified. And I should be able to simplify anything that's in here, but so just collecting ones that are kind of easier to add together. And so all I've done here now is simplify. I have not added anything to both sides. I haven't changed any values. I've simply rearranged the order and added the next thing I did was I factored out a common factor. Notice that all my denominators are divisible by 2. So I just factored out that denominator of 2. So I factored out 1/2. And check it out. Does this look familiar? Do you see it? It's the original, right? So this is 1 minus 1/2 plus 1/3 minus 1/4. And here it is again. Do you see that? So weird, right? But now it's getting multiplied by 1/2. So if this is the original series back here, I could just call it S. Really? So the sum of the series is equal to half of the sum of the series? Really? No, not really. That's why it's important. So we're wondering, why does it matter if a series is conditionally or absolutely convergent? In an absolutely convergent series, this would never happen. We wouldn't get that the sum is equal to half the sum. That doesn't make sense. So that's why it matters. So this was a conditionally convergent series. The order of these terms absolutely played a part in its convergence. Kind of cool. All right, so this fact leads us to the theorem of absolute convergence. If a series is absolutely convergent, then it's convergent. So what that means is basically if the absolute value converges, so does it without its absolute value. We use this theorem because sometimes it's easier to find convergence of the absolute value of a series than it is to find the convergence of the series by itself. And it doesn't even have to be for alternating series. You can use the non-alternating series too. So let me show you an example of that. So here we are with example number 4. I want to show you that the sum to infinity of the cosine of n divided by n squared actually is convergent. Now, we know this is not an alternating series. This goes cosine of 1 divided by 1 squared, which is a positive result, plus the cosine of 2 divided by 2 squared. This is a negative result. And plus a cosine of 3 divided by 3 squared. This is also a negative result. So it's not an alternating series because alternating series go plus, minus, plus, minus, plus, minus. And this one is not doing that. It's not alternating. I mean, the signs change, but not alternate. And it's also not entirely positive. A lot of our other convergence tests require us to have a positive decreasing sequence of numbers. And that's not what this is. So checking for absolute convergence is a way for us to kind of get around that since this is doing something so funky. So what do I know? I mean, hopefully a lot. I know that cosine, the absolute value of cosine, is less than or equal to 1. We can divide by n squared. We used this strategy previously to help us calculate using the squeeze theorem, right? Trying to create our function or our series so that it would look like what we had before. So this is a similar strategy. We've got the cosine of n divided by n squared. Its whole absolute value, including the denominator, is less than or equal to 1 divided by n squared. I just took this bad boy and divided both sides by n squared. Haven't changed the value, but here we go. So according to the comparison test, if the greater series is convergent, the smaller one is too. So what I really want to do now is check out this greater series and see if that converges. Because if I can get that to converge, then I'm going to be able to prove that the smaller one, the absolute value of the cosine of n divided by n squared, is going to converge as well. So is 1 divided by n squared convergent? By series, I know it is, right? The p-series test. With the p-series test, if my exponent here in the denominator was greater than 1, then I would have convergence. Since 2 is greater than 1 after all. Hence, since the sum to infinity of 1 over n squared is larger and convergent, then we know that the absolute value of the cosine of n divided by n squared also has to be convergent. Voila! Since we just figured out that the absolute value of the cosine of n divided by n squared is convergent, then by the theorem of absolute convergence, the original, sans the absolute value, also has to be convergent. So let's write that down. By the theorem of absolute convergence, I'm going to have to lift this up. The sum from 1 to infinity of the cosine of n divided by n squared is also convergent. And there you have it. Absolute convergence explained. I hope that that cleared things up and that you're feeling ready to do the homework on that. If you have any questions, definitely shoot me an email. And our next video is going to be on one of my all-time favorites, the ratio test. I hope you guys are ready to divide by n because we're about to party. I'll see you next time. Bye, guys.